This time, let's also try to show the rule for the Laplace transform of a quartic function or t to the power 4 function here. Of course, we are going to use the same idea or formula for identifying the Laplace transform. And in the previous videos, we also had the rule for t squared or quadratic function and t cubed, which is cubic function. And to make this video not that very long, so we're going to just automatically use the possibility of the existence of the cubic already proven in the previous video. So we will no longer provide here with multiple integration by parts, because for the proof for the rule for t squared, we had integration by parts twice. For our t cube 3 times, and of course we're going to stick with the integration by parts. We have here for our t4 would be 4 times of that. So basically, we will have here for the Laplace transform of your function t to the power 4 is equivalent to the integral from 0 to infinity of your e to the power of negative st and your function t to the power 4 dt here. Take note, this is what we're trying to show. So when you look at this form here, we're going to use the integration by parts. So the first part here is the identification by LATE. It depends on your idea or your function, which would be preferred as your u, and for your dv. So of course, our t to the power 4 is actually an algebraic function, and our e to the power of s negative st is an exponential. So by integration by parts, let our u be t to the power 4. That would mean for our du is 4t cubed dt. That would mean, because we will have here the integral of u dv, where we cannot integrate it, is equivalent to uv minus the integral of v du. So we need to use our dv to get our v. So the remaining item here, if we're going to pick this as u, so our dv is e to the power of negative st dt. By integrating both sides, e to the power of negative st dt, you will have here v. But to integrate the other side, you need here e to the power of negative st, a negative s, a constant s, because we're just integrating in terms of t. And to neutralize that, you have here 1 over s, or the negative of that. So that will actually be equal to 1. So we're not changing the actual form of the equation. This here, v is equal to negative 1 over s, e to the power of negative st plus c, or this time, let's just stick with that. That would mean the Laplace transform of t to the power of 4 is a combination of u, t to the power of 4, times your v, which is negative 1 over s, e to the power of negative st, integrate that from 0 to infinity, minus the integral of 0 to infinity of your v, negative 1 over s, e to the power of negative st, times your du, which is 4 times t cubed dt. Okay, let's do it step by step. What will happen for our first function here? If t approaches infinity, it's the t, not the s. You would know this is infinity, but for e to the power of negative infinity, automatically the result for that is just simply 0. As we apply 0, that with that would also be equivalent to minus 0. So we'll have the next 4 minus, taking this out and taking 4 out. Okay, so you will have, because that's also a constant, so you have here plus the negative of negative 4 over s times the integral of 0 to infinity of e to the power of negative st t cubed dt. Okay, so this time you are also going to use another integration by parts, because this can be integrated. So you'll be letting our u be equal to t cubed and our du be equal to 3t squared dt, and so on and so forth. But as I mentioned, since this is just equivalent to 4 over s, then the integral of 0 to infinity of e to the power of negative st t cubed dt, where this is actually the Laplace transform of your t cube, which we already have proven or shown in the or illustrated in the previous video. As mentioned, to make sure this video will not take that very long, because we are expected to have 4 times or 4 versions of integration by parts, let's simply introduce here the Laplace transform of this which is equivalent to that, is actually 6 over, if I'm correct, s to the power of 4. You can also review the previous video for this. At the same time, the methods that are done, or the methods that we use to determine this, or again, you can continue this method until you reach the 4 versions of integration by parts. But to save time, I have here 4 over s times 6 over s to the power of 4. In short, this is equivalent to 24 over s to the power of 5. This is the Laplace transform of your t to the power of 4. Okay? So this is the shorter way to identify that. So basically here, your Laplace transform t to the power of 4. And if we can actually see other expressions later on with t to the power of 4, simply use this for the Laplace transform of that. Now, I would just like to add here, the reason for me not dealing with the rest of the integration by parts is to introduce probably some concept here which connect all functions of t. Take note that if we have here the Laplace transform of t is equivalent to 1 over s squared. The Laplace transform of t squared is actually 2 over s cubed. The Laplace transform again of t cubed, as mentioned earlier, is 4 over s to the power of, sorry, my bad, for 6, sorry, 6 times s to the power of 4. And now the Laplace transform of t to the power of 4 is actually equivalent to 25 s to the power of 5. We actually have one rule for all functions of t. Okay, so if we have here the Laplace transform of t to the power of n is actually equivalent to your n factorial over s to the power of n plus 1. Okay, so our t is actually n is the exponent for the rule. So you will have here, say for example, if your n is 1, just like this one here, so you have 1 factorial which is just equal to 1, and s 1 plus 1 squared. If your n is actually 2 for squared, so 2 factorial is 2, and 2 plus 1 as an exponent of s is 3. If our n is 3 here, so 3 factorial is actually 6, 3 plus 1 is 4. And again, for t to the power of 4, you have here, your n is 4, 4 factorial is actually, sorry, my bad. This is not 25, right? I was actually, I had an error here, 24. Because 4 factorial is 24, that's correct. And then you will have here, 4 plus 1 is equal to 5. This is the general rule for t to the power of n. In short, if you are asked later on to get the Laplace transform of t to the power of 5, you don't need to use the actual process, including the integration by parts. You can simply use this formula. 5 factorial is 120 over s to the power of 6. You can verify this on your own time. This is the rule for the t to the power of 4, Laplace transform for that, or even this rule for any t to the power of n. Thank you very much for watching.